Okay, let's unpack this. We've got a stack of sources here, and it's some seriously dense material. We're talking quantum materials, advanced computation, nanotech.
It's a lot.
Yeah. And for most of us, quantum physics is this, abstract thing. It lives in textbooks and deals with stuff that's just ridiculously small.
Trillions of times smaller than a speck of dust, yeah.
Exactly. So our mission for this deep dive is to pull out the insights that prove the quantum world isn't just theory.
Right. It's actively blurring that line between the microscopic and the macroscopic world we all live in. We want to show you exactly where that weirdness is starting to bleed into your life.
And the sources kick off with a discovery that really, it just sets the stage perfectly. Let's talk about the 2025 Nobel Prize in Physics.
That was a huge moment, a pivotal moment. The prize confirmed something scientists had, been hypothesizing for decades.
Which was?
That nano effects, these tiny quantum interactions, can actually be observed on a macroscopic scale.
Wait, so not just in a lab with subatomic particles?
Not at all. They demonstrated it on a 10 by 10 millimeter scale.
That's massive in the quantum world.
It's enormous. And it proved definitively that these rules aren't just locked away in the theoretical realm. They scale up.
So what does that mean then? The central question we're looking at here is, well, if these effects aren't just microscopic, could they be the key to explaining physical phenomena that modern science still really struggles with?
It forces us to look at things differently, to use a quantum lens. The best example from our material is ball lightning.
Ball lightning, okay.
Yeah, it's puzzled scientists for centuries. Its sudden appearance, the way it moves so slowly, and how it holds together as this sphere of light for seconds at a time.
It doesn't fit.
It doesn't fit neatly into conventional physics, no.
Right.
The idea is that its very persistence, which requires a huge amount of energy packed into a small space, might be a macroscopic quantum effect.
Okay, so if we're going to try and spot these things hiding in plain sight, ball lightning or whatever else, we need a kind of field guide. What are the non-negotiable signatures?
There are three key hallmarks.
Sure.
The first is probability or non-determinism.
Meaning you can't predict it?
You can't predict it with certainty. In our classical world, you know all the starting conditions, you know the outcome. But in the quantum world, you can never say exactly where an electron is.
Only the probability of where it might be.
Exactly. So any big phenomenon rooted in that has to be, by definition, impossible to reliably reproduce.
Which leads right to the second signature, and this is the one that's it's the weirdest one. Observer dependence.
It is. The phenomenon fundamentally depends on the researcher, or just the act of looking at it. It's the core of quantum mechanics.
The Schrodinger's cat analogy.
That's the one. You cannot know if the cat is alive or dead until you open the box. The measurement itself forces one reality to emerge from all the possibilities.
And the third essential feature.
High energy density. For these quantum rules to show up on a big scale, like 10 millimeters or in ball lightning, you need a huge concentration of energy. Without that, the weirdness just stays where it belongs, down to the atomic level.
And this is where it gets really interesting for anyone listening. The sources point out that even things from fiction, telekinesis in a Stephen King novel, that kind of thing, they all share this quantum signature.
They do. They are impossible to reliably reproduce in a lab.
That unrepeatability, it isn't a flaw in the experiment.
No, it is the experiment. It's a huge sign of quantum non-determinism at work. If a scientist could, perform telekinesis 5 times out of 5 on command, it wouldn't be quantum. It would just be classical physics we hadn't figured out yet.
So that chaos is a feature, not a bug. But let's switch gears, because we're also using quantum physics to create incredible precision. Let's talk about the practical side, and nothing shows this better than the quantum logic clock.
Oh, the NIST clock is a staggering piece of engineering. It uses these exquisitely controlled aluminum ions. It is by far the most accurate clock in the world.
Okay, give us the numbers. How accurate?
The error rate is no more than 1 second over the course of 3.7 billion years.
3.7 billion. That's almost the age of the Earth.
Yeah.
What do we even do with a clock that precise?
Well, extreme time precision gives you extreme location precision. Think about your phone's GPS.
Okay.
Current systems are limited to meter-level accuracy. But compact versions of these quantum clocks could get us down to the centimeter level.
Centimeters. That changes everything for self-driving cars, for robotics.
Everything.
Incredible. And speaking of things that sound like science fiction, teleportation. We have to talk about that word.
We do. And let's be very clear, we are not talking about beaming people around.
Right. No Star Trek.
No, this is about transmitting a quantum state, the information a particle holds over a distance, instantly. and it's already happening.
How far have we gotten?
Well, in Europe, they've achieved electron teleportation over 100 kilometers. And in the US, a quantum particle state was sent over 44 kilometers.
So you're linking two particles and the information just leaps across space.
It leaps. That's a good way to put it. It's using entanglement.
And that ability to link information instantly and securely, that brings us to the holy grail of security, unbreakable codes.
Yes. Quantum cryptography. Today's encryption is based on math problems being really hard to solve. Just takes a lot of time.
Right.
Quantum cryptography guarantees security based on the fundamental laws of nature.
How does nature do that?
Because of that observer effect we talked about. Every message has a unique quantum key. If someone tries to intercept it, the very act of looking at the key, it collapses the state. It changes it permanently.
So you know immediately that you've been compromised.
Instantly. It makes eavesdropping physically impossible to hide.
That is a total paradigm shift. Now, beyond these high-tech applications, quantum insights are also changing. Physical materials, nanotechnology, what's actually being used today?
Oh, we're seeing an explosion of uses. Things like tiny nanomotors, artificial muscles, incredibly sensitive gas sensors. But the real revolution, in practical terms, is in composites.
Composites, you mean like plastics?
Exactly. Take a normal plastic compound. Now add a tiny amount, like 5% by mass of nanomaterial, like organic clay.
Just 5%. And what does that do?
It radically changes the material's properties. In the auto industry, it makes parts lighter and stronger. But in packaging, it creates films with incredible barrier properties.
How so?
The organic clay forms this labyrinth at the molecular level. It makes the film almost totally impermeable to oxygen or moisture. It extends the shelf life of food massively without making the package thicker.
That's quantum scale efficiency saving, I imagine, billions of dollars.
Easily.
Okay, that's a perfect real-world example. Let's move to the big one, the quantum computer. Why do we even need these? I mean, classical supercomputers are getting faster every single year.
Because they're about to hit a wall. A computational barrier.
Okay.
And it's an absolute wall built on exponential growth.
Explain that for us. What's the exponential wall?
If you're modeling a complex molecule, adding just one more electron spin to your calculation doubles the complexity.
Doubles.
So if you want to model, say, 300 electron spins, you're looking at 2 to the power 300 possible states. That number is bigger than the number of atoms in the known universe. No classical computer ever can solve that.
Okay, so that's impossible. And the quantum computer gets around that because of the difference between a bit and a qubit.
That's the heart of it. A classical bit is simple, 0 or 1. Physically, it's pretty big, thousands of atoms. A qubit, a quantum bit, is tiny, a single charged atom.
And it can exist in a superposition.
Yes. It's not just 0 or 1. It's in a weighted combination of both at the same time. Like 30% 0 and 70% 1.
I love the analogy the source used, the Domino's pizza.
It's a great one. Until you open the box, the pizza exists in a quantum superposition of being a margarita, a pepperoni, and a Hawaiian all at once.
And opening the box is the measurement. It forces it to become just one of those. I wish my pizza did that.
Huh, right. But superposition is only one pillar. The other, just as crucial, is entanglement.
Einstein's spooky action at a distance.
The very same. You take two quantum systems, let them interact, and then you pull them apart. They stay connected instantly, even if they're light years away from each other.
So if you measure one, you instantly know the state of the other one.
Instantly. And that non-local connection is what gives quantum computers their power. They're not just calculating one thing at a time, or even two things. They're calculating this huge web of interconnected variables all at once.
Which leads to the race for quantum supremacy, performing a calculation that's just impossible for a classical machine. Where are we in that race?
Well, a starting gun really fired in 2019. Google's Sycamore processor, 54 qubits, did a calculation in 200 seconds that they claimed would take a supercomputer 10,000 years.
Now, IBM disputed that, right?
They did. IBM said their supercomputer could do it in about 2.5 days. But even so, the point stands. The advantage is real, and it's growing.
And where are we today? What's the current state of the art?
IBM now has systems with 433 qubits. But the general consensus is that for a truly universal, useful quantum computer, we're going to need something like 1 million physical qubits.
1 million. So we're still in the very early days.
Very early days. Which brings us to the biggest hurdle of all.
Decoherence.
Decoherence. You have to keep those qubits totally isolated from the outside world to maintain their superposition. The tiniest vibration, a stray magnetic field, anything.
And the whole thing collapses. The calculation fails.
It just ends. That's why you see those incredible chandelier structures. They're basically the world's most sophisticated refrigerators using extreme cooling and magnetic shielding to protect the qubits.
Okay, let's pivot to the other side of this. Computational physics. How do scientists actually use these ideas to model things, and why do they keep hitting roadblocks?
It all comes down to one core equation, Schrödinger's equation. And the thing is, its basic form looks simple, but solving it exactly is impossible for anything with more than one electron.
So for basically any useful atom or molecule,
Right, so you're forced to use approximations and computational methods.
which is where the ab initio approach comes in.
Ab initio, from first principles. It's incredibly powerful because you don't need any experimental data to start. All you need is the elements involved, where their nuclei are, and how many electrons there are.
So it's purely predictive. You can design a molecule on a computer and know its properties before you ever make it in a lab.
That's the goal, yes, and it can be highly accurate. But the most precise ab initio methods have that same exponential scaling problem. They're fantastic, but they can only handle tiny systems, maybe 10 atoms or so.
So how do you model the big stuff?
Hmm.
Proteins, materials, things with thousands of atoms.
That's where a method called density functional theory, or DFT, came in and just revolutionized everything.
Okay. What does DFT do differently?
Instead of tracking the impossibly complex state of every single electron, it focuses on one much simpler property, the overall electron density.
And that's easier to calculate.
Infinitely easier. Electron density is just a function of 3 spatial coordinates, no matter if you have 10 electrons or 10,000. It turns an exponential problem into a polynomial one. It made modeling large systems possible.
It sounds like the perfect solution, but are there still limitations?
Oh, yes.
Yeah.
DFT is a workhorse, but it struggles in a couple of key areas. First, describing dispersion forces.
Those are the weak van der Waals forces.
Exactly, the weak attractions between molecules. If you can't model those accurately, you can't really model organic chemistry or the behavior of gases properly. The other big issue is calculating the band gap in semiconductors.
And the band gap is critical for electronics.
Absolutely vital. If your simulation gets the band gap wrong, the real-world solar cell or transistor you build based on it just won't work as designed.
So modern computational physics is a big balancing act, a trade-off.
It's a constant trade-off between accuracy and size. The high-accuracy methods give you incredible precision down to 0.1 kilocalories per mole, but only for a handful of atoms. Methods like molecular dynamics can handle 100,000 atoms.
A huge system.
But your precision drops way down, maybe to around 10 kilocalories per mole. You have to pick the right tool for the job.
So bringing this all together, what's the final takeaway for you listening to this? The quantum computer. It's not going to replace your laptop.
Not at all. It's almost useless for browsing the internet or writing an email.
Its power is incredibly specialized. It's for tackling those exponential problems where classical computers just give up.
Things like complex financial modeling, optimizing a global shipping network, or designing that perfect drug molecule by simulating every possible interaction.
So the future isn't a quantum desktop. It's more like a quantum server in the cloud that you access for very specific tasks.
It's a powerful supplement, yeah. You'll connect to it only when you have a problem that's literally impossible to solve any other way.
And that raises a final sort of philosophical question to leave everyone with. The most important function of all this might just be helping us understand the laws of physics themselves.
I think so. It leads to this really provocative idea, the very math we're trying to build into these computers, superposition, entanglement, probability. It suggests that the entire universe can be viewed as one gigantic quantum computer.
A simulator.
A simulator, constantly calculating and defining itself into existence, moment by moment.